Thank you very much. Thanks a lot for the opportunity to speak. Okay, so let me start by recalling the two fundamental equation in quantum integrability. So, which is the Yang-Baxter equation and the reflection equation. So we start with R, and so this is a function with value in endomorphism of a tensor product of a finite dimensional vector space, and this is called an R matrix whenever it satisfies the Yang-Baxter equation. And then instead, the second player here, which will be the main character of the story, is the K-matrix, and the K-matrix is going to be also a function in a complex parameter, and this is going to take value into the endomorphism of just a single copy of V. And then it satisfies this reflection equation that is a quadratic. So the Yang-Baxter is cubic, and instead the reflection equation depends upon the choice of an R matrix, and then it's a little bit different. So this is, sorry, I never remember the indices. Okay. And then this equation appeared again studying one-dimensional quantum integrable system. So roughly one can think of describing particle moving on a line, and then this is what the Yang-Baxter is describing, the interaction of particles moving on a line. And then the reflection equation was introduced about something like 40 years ago by Ivan Cherednik, and this is describing instead frankly, okay. By Schirani and Cherednik, and describe instead what happens on an half line. So we have, in fact, we have a wall, and so these particles are bouncing against this wall, and this is what is describing. And then, in fact, I will be interested not just in this one. So there are several variants of this equation, and then in your paper, though, in Cherednik paper, there is a variant where now we have actually not just one R matrix, but in fact, we have three R matrices, which are labeled by these indices. And then each of these three operators, they satisfy some kind of mixed Yang-Baxter equation. And then this is going to give you a system of compatibility. And then, in fact, to be complete, still there will be another version where even in this case, there will be two operators corresponding to K, and this will correspond to having two boundaries. And this is what yeah, exactly. So, so again, very old story. So what we want to do is essentially to find some systematic representation theoretic approach to solving this equation and producing systems. And then very old story. We know that roughly the Yang-Baxter equation, we can attack it by using the representation theory of quantum loop algebras and Yangians. And this was due, let's say, FRT and Drinfeld. So this was known since the work of Adeyev, Reshetikhin, and Takhtajan, that basically said in a certain sense that having an R matrix is more or less the same thing of having a quantum group. And then Drinfeld provided sort of this systematic approach to producing R matrices, spectral R matrices, depending on this parameter, using the finite dimensional representation theory of these two algebras. And then, in fact, here let me comment again on this dependence of the parameter according to what is the analytic property of the matrix coefficient of my R matrix. I can call this are matrix, this I can call it as a meromorphic function. If the matrix entries are meromorphic, are rational functions, they're rational. Or I can think of this parameter to be just a formal parameter. And then in that case, would be a formal R matrix. And then the Youngian and the quantum loop algebra, they were way of producing rational solution of the Yang-Baxter equation. To be more precise, this particular form, which is a multiplicative form of the Yang-Baxter, really correspond to the quantum loop algebra, and the Youngian is some kind of rational degeneration of those. And instead, what happens on this side, and so on this side, so as we said, that these were introduced in the 80s, and then almost immediately it was kind of clear that kind of analog approach in representation theoretic approach to the reflection equation, this should arise from some co-ideal subalgebras. Let me say of fixed points. In quotes. And then this corresponds to indeed what are these affine quantum symmetric pair, which I will mostly talk about today, and then on the Youngian side to twisted Youngians. And so while for the Yang-Baxter equation progress was very, very fast, so end of the 80s, we already had, beginning of the 90s, we already had this completely systematic approach to producing solution using the representation theory of quantum loop algebra and Youngians. And then from there we started, and even today we're still finding more and more structure. So for the reflection equation, the progress was very different and much slower. And so the expectation was kind of clear that actually this algebraic object was supposed to control this theory. And then I guess another thing that was clear is that this kind of Yang-Baxter theory is something like an A theory, even if we think about it in terms of break groups. The Yang-Baxter equation is something like a representation of a break group of type A. And then this story with the reflection equation should be some kind of type B theory of quantum groups. And so even because, again, from this point of view, this reflection equation, you can think of it as a quadratic relation in a break group of type B, which is the break group of the cylinder. So, but I was saying that the progress was on a very different pace, and in particular, while here the theory is kind of very homogeneous, there is always a parallel between what happens on the quantum loop, what happens on the Youngians. What we know now on this side is much more scattered still. So now there is a big boom on this area. There will be a lot of developments, and it's kind of surprising that it took 40 years to get here. So just to give you an idea, as I said, I will focus mostly on this aspect, but just to give you a comparison of what is known on the side of twisted Youngians. So twisted Youngians, again, they were also introduced by Olshansky, Nazarov, and Molev, and then in something like an FRT definition of Youngian. So instead of using this RTT presentation, they were using an RS-RS presentation that is mimicking the reflection equation. And this was generalized by Delius, McKay, and Short. And then some other more general definition appeared by a work of Béliard and Regelsky only something like 10, 15 years ago. So there was a big gap. And now we have, by the work of Weichan Wang and collaborators, now there is a kind of a new definition of twisted Youngians that relies on something which is similar to the Drinfeld presentation of the Youngian. So by the work of Weichan, actually now there is a kind of a complete, at least presentation of what these algebras are supposed to be. So here was kind of a long path to get to the definition of the algebra. Here the algebra is kind of clear. So this is the first difference that we have. And then in contrast, so what we have at the level of K-matrices for twisted Youngians. So during the 90s, there were a lot of examples that were of particular representation showing that the twisted Youngians are supposed to be there. But in terms of producing some kind of systematic approach for the K-matrices, for the Youngans, we still don't have almost anything. And so I think something remarkable to mention is the work of Lee from 2018 and Nakajima from earlier this year, where basically what they were doing is something like generalizing Maulikov-Gunkov approach to the R-matrix of the Yangian. So basically, they use cohomology of quiver varieties in order to construct the algebras and produce the R-matrices. And so here the approach is actually to consider some fixed points in the quiver varieties, and then studying the cohomology. This actually leads to geometric interpretation, geometric construction of K-matrices. And then another results is due to Bittelstone and Skinner. From 2019, and this is instead is giving a boundary analog of the result of Costello, Witten, and Yamazaki, where they produced an approach to the R-matrix of the Yangian in terms of four-dimensional Chern-Simons theory. And so here, the theory again is in this approach is a four-dimensional theory, and here the theory lives on a Z2 orbifold, four-dimensional Z2 orbifold. And I should say this is not complete. It's something like at the first approach, first iteration, like modulo H squared, but it's still showing that the theory produces something like K-matrices. On the other hand, on this side, there is no algebraic interpretation of how the K-matrix is supposed to exist, which again is what instead we're going to discuss here today for the quantum symmetric pairs. So, in fact, from this point of view and from this parallel, basically the only thing I will be discussing today is something like the analog of Drinfeld theorem for the R-matrix of the quantum affine algebra. Then I will discuss it for affine QST. Okay. So let me try to then discuss what this object is supposed to be, these quantum symmetric pairs. This is taller than me. And so what we have here, the construction is the following. As I said, for some reason we want to look at co-ideal subalgebra of fixed points. The idea is the following: I get G to be a Kac-Moody algebra, and then theta is what Katz and Wang defined like an involution of second kind. And this basically simply means that up to automorphism, I can describe this involution in this way. So where now this first term here, this is just a rescaling. Rescaling on the root spaces. Then tau is a diagram involution. Omega is the Chevalley involution. And this, which actually I should probably use some tilde, this is going to be the lift of the Weil group action to the Lie algebra using triple exponential. And this WX, this is the longest element in the parabolic Weil group that correspond to a set of something that we refer to as the black nodes. So this is a subset of nodes in the linking diagram, and this is of finite type. And this datum that we have, so this X tau is called the Satake diagram. So this is a decoration of the thinking diagram when I'm gonna denote some of the nodes with what I will color black, and then I have an involution on the thinking diagram. And the X and O, they will satisfy some compatibility condition. And let me say just very, very roughly that essentially, I mean, this is not really true. This is almost, this is more or less a lie, but let's say that this is more or less equivalent to say that whenever I restrict to the Lie subalgebra that correspond to X, then this is the identity. Okay. Plus, there is some extra technical requirement about the compatibility between X and O. And so what we want to focus our attention on now here, it would be just the fixed points with respect to this. For now, let me use this subindex JKM. So this is going to be fixed points with respect to this involution. And
can you make it more?
I will get there.
Oh.
But in general, in a certain sense, this will be kind of don't think it too much. And then if you need a concrete example, just put simply everything is going to be one. So the involution you just consider a trivial involution. X you consider the empty set, and now you just have the Chevalet involution. So you can simply take fixed points with respect to Chevalet. So indeed, from this point of view, for instance, kind of the most illuminating example in a certain sense is when you take SON inside SLN, which again is Chevalet, or in fact inside affine SL2, you have fixed points with respect to Chevalet, they give you the Onzager algebra. And so, as I was saying, this is interesting to take fixed points, and the reason is that, in a certain sense, because if you look at the Poisson-Lie side, then we consider a Poisson-Lie group G, then we can consider a fixed point subgroup, take the corresponding symmetric space. We want the symmetric space to have this Poisson structure, and this means that actually the smaller matrix has a compatibility with the involution, and this actually suggests that this will be producing a K-matrix. So in a certain sense, that's why we focus on this basis. Okay, and so now what we want to do is to essentially to lift this picture, and so we want to quantize this fixed point subalgebra. And so everything more or less kind of immediately quantize if we move from our Kac-Moody, and then we go into the Drinfeld-Jimbo. And so for tau and omega, this can lift automatically. They lift automatically to automorphism of to involutions actually of my quantum group. And then here, this y, as I said, this is a rescaling, but I'm going to think of this as some kind of parameters in a certain sense. So I can also lift it up to something. Not yet. I'm just Kac-Moody. This is like a Drinfeld-Jimbo quantum group for a Kac-Moody system. Okay, so it's just but let's say simply that there won't be any parameter. It's still a constant picture. Okay, so this is what it is now. But the construction of the algebra then basically applies by simply considering an affine Lie algebra, and then you do exactly the same construction. Okay, so basically as I said here, the only thing that kind of change is that. So this guy here, well, let's say my triple exponential, I will then replace it in this quantum group picture by some operator S theta, and this is basically a modified quantum Weyl group operator that corresponds again to WX. Okay, so I take WX, I take a reduced expression, and then I consider the Lustig operator, that the quantum wide group operators corresponding to the simple root. I take the corresponding product, and then this will be some Cartan modification of that, which is not particularly relevant. And then now I can define my lift, so my quantization of theta. So this would be, again, I will have the action of this guy. So conjugating by S theta is going to produce an automorphism of the quantum group. Then I will have omega and tau as before. And then now I will have this rescaling. And this rescaling becomes part of the data. And this would be like a parameter for us. And then by using this lift, now basically what I do is that I consider the subalgebra here is the subalgebra which is generated by those elements Bi, which are simply defined as something like fixed points. Let me just say I and I. Okay. So in fact, there would be something more and UQGX. All right. So basically, what it means is that I'm just looking at the initial fixture. So in the fixed points, I have the full GX. So I just take the full quantum group corresponding to GX, and then I put it into this subalgebra. Oh, this one? This one, as I said, so basically what you do is that you consider the Lustig operator. So you have the quantum triple exponential of. Yeah, eventually when I do add S, I get the internal action, right? So yes, right. It will be, yes, so this denotes actually Lustig internal action, internal break group action, but it would be relevant for me to just consider this. Yeah, exactly. Okay. Okay, and so now we take this subalgebra, and then here we have a theorem. This is due to Letzter. Was in 99. And Kolb. And this is saying actually, so what do we have? That this algebra is co-ideal. And in fact, this is unique in a certain sense. What we have is that this Q limit gives actually the fixed points and is unique in this sense. Okay, and when I say this is isomorphic to some B, it means that again, as I said, that we have one parameter here, which is this gamma. This is going to be a bunch of complex numbers, or numbers in our field, and here I have a second family of parameters. So I have in fact a very big family of subalgebras. They all satisfy this property that they quantize the enveloping algebra of fixed points, and every maximal co-ideal in the quantum group satisfying this property must be isomorphic to one of those. So this can be defined in general for whatever Kac-Moody. So in particular, we can define it for affine algebra. Okay, and so as I said, first we solve the problem in this setting, and then we go to the affine. So here what we have is the following. I'm going to use a slightly different notation. So now I will put psi is going to be just the inverse of this map. And then this element J, then I'm going to use use in a second. This is actually, well, let me see, this is a modified R matrix corresponding to the, so this is the R matrix of UQGX. Okay, and when I said modified, it always means that there is a Cartan modification of this object. Universal, yes. Okay. Okay, and so what do we have? I mean, this is actually something that justifies also why we want to consider this algebra. It's basically because this theorem is true. So we see that there exists a unique element of this form. This is K. So let me write it like this. So this is going to live in. So this is my weight component of, let's say, it's my B plus, and then I take, actually this is going to be N plus, and then I take the weight component corresponding to that. So I have a series in the positive part of the quantum group that grows with the weight. And then there is a unique element of this form that satisfies this twisted intertwining equation. Where B lives precisely in this subalgebra B. So if we try to solve this twisted intertwining equation, that automatically this means we see that actually there is a unique element that satisfies this equation. This part is done very much in Lustig style. So meaning we look at this intertwining equation, we impose the form of our solution K, and then we hammer it down trying to solve it. And then you can prove that this actually is going to give you a recursive system which is consistent, and so the solution exists is unique. And moreover, yes, but actually the reflection equation follows. So now it's automatic. So we found this unique element. And so now what also we can prove once we have the element is that actually this element is going to satisfy a specific coproduct identity. Where here my R psi is going to be like that. And since I have this coproduct identity, then you can prove in 2 lines by using the same game of conjugating delta with delta hop, that actually you can prove in 2 lines that this object satisfies something which looks like Ivan reflection equation. So here we get R21 psi psi. Yeah. And so you see that with the.
But these are really not belong to this idea, but generally for Lustig, that's for the whole thing, right? This integration.
Yes.
Like the way you speak to
Yeah, the intertwining equation you mean is constrained to B. Yes, right. But this one you see actually that if you try for SL2, you will see that you get an element. Yes, even because if you don't impose it, you want something completely general, you don't find it. You get different solutions. Yes, exactly. And so as I was saying, you can notice that in this form, we really get that this is how we can interpret these signs, plus and minuses. Basically, the idea is that when I think about my K matrix, this is also why this is called the K matrix, is that actually I have my puncture, and then the operator that I get, it should be something that goes around the puncture and then goes back to the same place. But the point is that I start from my V, and when I'm back, after I bounce my head against the wall, I'm not the same as before. And so something changed. And this change actually algebraically is represented by twisting by this automorphism psi. So this is how this psi is actually important for this aspect. Okay. And just as a comment, I mean, the theorem in this form appeared in my work with Bart Vlaar from 2020, but in a certain sense, we were actually using a lot of heavyweight lifting that has been done by other people before in showing that this equation can be solved. So in particular, there was Balagovic-Kolb in 2016 that on the other end was finite type. And then they were also generalizing some work of Bao and Wang from 2013 for a specific example in type A for SLN. So Bao and Wang really introduced this kind of concept, even though they were not really caring about the coproduct identity, but this is how they were trying to solve this identity, more or less, in their paper in type A, and then Stefan and Martina generalized it to every finite type quantum group. And then with Bart, we realized that their approach was not actually ready to be generalized to Kac-Moody. We needed to massage it a little bit, modifying it, and then we could extend it to Kac-Moody. And once so this actually is why the difference is that now we really get this psi and this j are kind of fundamental to appear in this form. So once we have the picture in this Kac-Moody setting, then going to affine is more or less a piece of cake. So what we do now is that indeed we consider G to be, let me say, what do I want to use? I want to use maybe G hat. Yes, G hat. So we now consider this case, and you know that when I have an affine Kac-Moody, the affine Kac-Moody comes with the loop algebra. Then there is a central extension. Then there is a derivation, and then if you want to consider finite dimensional representation, there are two things you need to do. You first cut out the derivation. That one you don't consider it, and then if you are finite dimensional, the center is automatically acting like 0. So in this case, what you get is a category. Let me denote it by just C, which are finite dimensional representations over the quantum loop algebra, which I'm getting from the quantum affine exactly in the same way. I forget about the derivation in the quantum group, and then I mod out by the center. And this is what the quantum loop algebra is. And then I take these finite dimensional representations. And then this category of the representation theory of this guy, so where does the spectral parameters appear? The point is that we have a shift operator so this can be either numerical or formal. And what it does, this shift operator, this will be the homogeneous shift operator. So basically, I take my EI generators, and this is just going to shift in Z only the affine node. So whenever I'm on the affine node, I shift in Z. For E, I shift in Z inverse for F, and then I don't touch the Cartan. So why it is useful to consider this this object? So here, the point is simply that, for instance, I would like the matrix to act. So I would like to take V and W in C, and then I would like to consider an action of the matrix on this tensor product. And now the point is that this has no reason to work. So this is going to be some infinite series. I don't have any highest weight condition that guarantees that this series is going to truncate. So this does not make any sense. So the only thing that I can do or the thing one thing that I can do is actually to replace R with some formal shift. And then at this point, I can consider a formal operator on something that I would denote like this. So my WZ, my VZ is just going to be the pullback under the shift. And so this at the moment is going to be just formal. This is going to be an infinite series in Z, a power series in Z. On the other hand, for every fixed power of Z, the coefficient is going to make sense, so I can evaluate. And so I get, for instance, I get something which is a formal solution of the Yang-Baxter equation. And then this was proved by various people. So by, I guess, Drinfeld stated it, and then it was proved by Kashtan Sobelman and then Chari, that this tensor product, V tensor WZ, this is actually, is called, one says that this is generically irreducible. So it means that now if I shift in Z for almost every value of this complex parameter, this tensor product is irreducible. So the behavior is wildly different with respect to the usual Kac-Moody theory. And hence, what it follows is that this formal R matrix break down into a product of a rational operator and a meromorphic functions. So here, we are going to follow more or less the same path. So what we do is that, again, we define our KZ yeah. That's correct. So what just said in other ways, actually the points where the tensor product is reducible is actually controlled by the poles of these armadas. Yes, that's right. That's right. Yes. Okay. So what we're going to do now in our case is to consider this shifted K-matrix, which we can look at as a formal operator, and therefore actually now in this case also we immediately get a formal solution of the reflection equation. And the way we understand it now, this is actually going to be some intertwiner with respect to B. So, and this actually, if I look at the intertwining equation and then I evaluate the intertwining equation, this would be something like this. But now, on the other hand, if I look back at about what is the definition of my shift, all those shifts. So here I'm making some simplified assumption. So I assume that the affine node is fixed by tau, and the affine node is not in X. These are not really necessary, but they're useful. And so if now I look at my twist psi, which is the inverse of this guy, what you see is that tau is going to pass through. Chevalier is going to simply send the shift in Z to the shift in Z inverse. And this part, which is also supported in X, is going to pass through the homogeneous shift. So that now this guy is simply V psi shifted in Z inverse. And so now if you look at this, this is how you understand the slightly different behavior of the parameters in the reflection equation with respect to Yang-Baxter. In Yang-Baxter, you just have a multiplicative behavior. But then if you look at the reflection equation, the meaning is that whenever you apply K, your parameter gets inverted. And so what you get is that now your secondary matrix, instead of being Z over W, would be instead Z times W. Yes. 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 Yeah. So you mean for this guy? So at the moment, I'm looking at this only as acting on the quantum group. On the quantum group, I have no problem. Yeah. And also in a certain sense, yes, yeah, you're right. Yes. So in fact, what I want is it seems to pass through, right? So this is only the inner action on the quantum group. So for the moment, there is no no problem. Okay. Okay, so this is what we get. So we get this B intertwiner here, we said. And so at this point, we get, so let me go back. Well, let me keep the reflection equation there. And so now at this point, we are interested in understanding if we can say something more. This is formal, it's fine, but we would like to say something more. And so if now we take V and C, and then we suppose this is an irreducible. So these are irreducible finite dimensional modules over the quantum loop algebra. Then what we have, again, that Vz is generically irreducible over B. So this is actually now giving us the counterpart of this generic irreducibility of the tensor product. And then for the reflection equation, the key will be restriction. And so even in this case, what we have is that if we restrict to this algebra for almost all complex parameters, the representation remains irreducible. So, and then this property, this is actually, I should have stated as a one-dimensionality of the n space. And then this is going to give us a unique factorization. So this is very obvious consequence of my K matrix as a function Z, and then I have some polynomial operator. So this one is going to be here, and this is going to be a non-vanishing operator. And this belongs to Z. And so again, this part is slightly is the most technical result that one needs to prove, but you can also think it in this way. Of course, I erased it, but I can think of this QSP of being some kind of a modified nilpotent subalgebras. So if you think about the representation theory of quantum loop algebra, there is also an easy result is that if you restrict to the Borel and irreducible to the Borel, this remains irreducible. But then also you can refine it further and say, even if you refine it to reduce to the positive part, it still remains irreducible. And so this result here is some kind of modification of these results due to Chari. Because I'm taking out of the poles and then I. Yeah, this is much more trivial in a sense, but. Yeah, you take out everything you can. In this case, there are no poles here, Wafang. So. Right, but then at the roots of the polynomial, this operator will vanish. Right? So the point is that this is never vanishing operator. So in that sense, again, it's very, very trivial. It's not in deep. And okay. So in fact, I mean, we got this is not particularly enlightening, but there is something more precise that we can do. And so we have an assumption, so assume that our irreducible has a behavior like that. So what does it mean? It means I take my finite dimension and then I pull it back by Chevalier. And then what I'm requiring is that this must be the same thing as taking my reducible and pull it back by the automorphism of the finite type Dynkin diagram corresponding to the quantum affine that correspond to the longest element in the Weil group, in the finite Weil group. So this is a result that also you have on finite dimensional representation in simple algebras, right? So you have the Chevalier X like this permutation of the weights according to the action of this longest element. And so if this condition is verified, and this is verified up to a global shift, then in two particular cases, we get something which is more interesting. Whenever my shift tau correspond exactly to this, an extension of this involution, then I can find a unitary solution of the standard reflection equation. And the standard reflection equation means that the sign, in a certain sense, disappear from that equation. The psi becomes trivial on my representation, and then whenever there will be no minus and plus. There will be just one R matrix. Yes, exactly. And then when tau is the identity, I also get a unitary R matrix, but now I will have the, we call it the transposed reflection. Yes. And so in this case, it is actually the same equation. Yes. So in one case, V psi is isomorphic to V, and in this second case, V psi is isomorphic to its dual. Yeah. Oh, this is only when this condition is satisfied. And so this condition at first may look a little bit restrictive, but sorry, let me say just another thing. In this case, actually, I move from a polynomial equation, then a polynomial operator, to a unitary operator. So it means that actually now there are poles appearing in my operator, and these poles, they do detect in part the points of reduction of my restriction. So exactly whenever I have pole on this K matrix, then the representation is reducible under restriction. And the second thing is that yeah, exactly, when this is true, so this condition here so these are actually the two equations that are most common in physics. This is why, in a certain sense, we actually like to find explicitly this example. Most of the known example of solution of the reflection equation is for one of these two equations. And so this works for small modules. Level zero, right. So as I said, small modules, this means that this is an element in C, which is irreducible over the finite quantum group that sits inside. And these are very sparse. So this has been classified for fundamental representation, and then I don't think that much more is known. So, but in this case, this works. And then in general, this works for every Kirillov-Reshetigin modules. Also, in this case, actually, they do satisfy an equation like that. Kirillov-Reshetigin modules, if you remember, if you have this Drinfeld polynomial, it means all Drinfeld polynomials are trivial except in one node. And then in one node, they have a prescribed form, which is compatible with this condition. And then, in fact, in type ADE, this works for, in fact, for every And in type AD, this is true whenever my reducible module has a kind of a symmetry in the roots of the Drinfeld polynomials. So in particular, at every node, I want the roots of this polynomial to be invariant under this transformation. And the transformation must be valid for for a single C that works for every node. Okay. So if I have this condition, then type AD, I can apply to all those guys. Okay.
He is very special.
No, sorry. This is actually is more or less the same. It's going to be the same. It's going to be the same. So, well, that one must be true for some A, right? So you need to find, yeah, exactly. Okay. So now this actually gives us some kind of general systematic approach to that equation, but we would like to go a little bit further. And then from a certain point of view, again, our goal there was to understand Ivan and Evgeny Skilani paper from the 80s and to really have a kind of an explanation to this paper from the representation theory point of view. And there is indeed in Skilani paper, there is another aspect that is considered when he studies this integrable system with non-periodic boundary condition that at some point introduce a transfer matrix, which is a standard construction you would do in this one-dimensional stuff. And so the idea would be, okay, so how can we see Skilani transfer matrices from this theory? And so there is an extra step that one needs to do, which is from K, which is, as I said, this is an operator in one leg. Now we can cook up a two-leg operator, which now will have more the flavor of an R matrix, which is kind of a sandwich of my one-leg K matrix with two R matrices. And this is very much also still the same picture that I wrote before, in fact. And something that you can prove on this with respect to this operator is that in general, this is going to act on every tensor product of a B module times a U module. So remember, the fact that B is coideal means that the category of representation of U acts on the category of representation over B. And so here, when I take this sandwich operator, I can prove that the left leg is supported in B, and therefore I can use it to act on any module over the quantum symmetric pairs. So this now is going to give me a slightly different operator. This would satisfy as well a bunch of identities that are been the framework correspond to the reflection algebras introduced by Enriquez. And this is also saying that so there is also some nice theorem by Stefan Kolb and Milan Yakimov. And this year there is a kind of follow-up of their theorem that they're basically giving an interpretation. So they can interrelate essentially this K with the quasi K matrix, with the quasi R matrix. Sorry. So basically they have a formula so that if you simply give them the formula for the quasi-R matrix, they will apply a special map, which is called the Lester map, to the left leg of the R matrix, and this is going to produce this guy automatically. So this is going to give giving some kind of new flavor of this thing as some kind of canonical tensor. Not still clear in which sense BK is supposed to be a canonical tensor, but anyway, we are there. Okay, so now that we have this K matrix, this tensor K-matrix. So the temptation, if I want to try to simply consider this algebraic approach to transfer matrix, would be quite simple. So I have an option here. Where I can do this. And so I would like this map to be something like, let's say that I'm doing it with let's say that I'm already working still in the affine case, where everything is still okay. And then if I do something like this, then what I would like to have is something like that take as an input an element in the Grothendieck group of my category C, and spits out some element, which in this case is going to be in BZ. And this, remember, is going to be commutative. So this is going to be, the image is also going to be commutative, and then you can start to argue. Now, what happens is that actually this thing, like this, does not work. No. And similarly, on the other hand, this is the other interesting thing, is that it works, but not so immediately. And then I can do another. Yeah, no, I know. That's why it's interesting. And I can do a second thing. No. So, and the second thing here would be that I can try something like that. Okay, so this is going to be, again, let's say B plus, and then I'm here. So the first thing is that, again, not even this setting actually works. But the point is that there is something interesting, is that when I have this operator, this is asymmetric with respect to the usual story with the R matrix. So now it's interesting that I can get two different kind of transfer matrices, maybe. And one will actually study the Grothendieck group, the Grothendieck ring of the quantum loop algebra inside the QSP, some beta subalgebra in the QSP. And conversely, here I can get maybe some kind of Q character for the representation theory of the QSP. Now, as I said, those things literally they do not work. So there are two adjustments that one can try to do. So this Q character story, there is a series of papers by Jean Rongli and Tomasz Przyzecki, where they actually consider not really this map, but it's like they jump a step, they go directly inside the loop Cartan. This is exactly the procedure that the Frankel-Reshetigin did. And so they construct a map. This is some kind of the Harish-Chandra map. And they construct a map by using some kind of abelian K-matrix, which is not clear if this operator that they define is really related to this construction. They define something ad hoc. So they define ad hoc this abelian operator, but they were able to find some property of these boundary Q characters. And then I would say that at some point, anyway, you stop, because we know so little of the representation theory of these algebras that it's hard to see what happens. Okay, so what about instead in the last minute? What about this correction? So in this correction, that, as I said, for us is really motivated by understanding Skilanin paper. And indeed, the Skilanin doesn't consider an object like that. But what you need to do is instead to imagine that you really are into something which is like a double boundary situation. And so this tensor K matrix, you need to correct it by an auxiliary single K matrix, also on the right leg. And then if you do this construction for a specific K matrix, that you can cook up a definition, actually a precise condition that this K tilde is supposed to satisfy, and then this will work And this will be producing actually our ring map from quantum groups into this side. And here there are only two things I can say are kind of interesting. This works, but the point, yes, but that was also before. But now the point is that really here we are trying to understand that Skilanin did some kind of linear algebra magic in his 1988 paper. And here we were able to give the algebraic understanding of what was happening there. So there is something you need to use a little bit more structure and throw into the balance of the category and so on. But you can translate it and make that trick work for whatever representation. So this is going to give you now this ring map that we expect exactly to produce some possibly new beta subalgebras in this affine QSP. And then I will stop here.